Hi, this is Math 408, Lecture 22, L functions and sphere packing. So what we're going to do today is we'll finish up and actually give a construction of something that is a modular form. Just because we spent an entire class talking about a construction that was a natural thing to try, but it failed, let's actually visit and try to find something that works. And this is really a good example of what we're going to be looking at for a lot of the next few weeks. Although our classes continue after you guys go home for Thanksgiving, right? It just all becomes remote. Okay. Where it comes down to, can we find an object with given properties? So there's a couple of conditions for what something is for it to be a cusp form. So the big things we want. Yes?
The Zoom background's still on, so we can't see the board.
Oh, you can't see the board?
See the Jeopardy one. Maybe.
Interesting. Well, here, I will. Okay. So how's that?
That's good.
Okay. So hopefully this will be visible. Okay. So gamma is always going to be in either PSL2Z or SL2Z. We want f of gamma z to be CZ plus d to the 2k f of z. So we have some kind of transformation properties. We want f to be holomorphic on H. This basically just means it's complex differentiable. We are often going to have some conditions on the boundary. I'm not going to really worry about those right now. And then what I want to do now is talk about a specific option. So what we'll do is we're going to look at an Eisenstein series. And so it's been a while since we've played a lot of games with lattices. We're going to do a lot with lattices today. And so we will define, there's a couple of ways of doing this. So we'll take some lattice lambda, and we can look at what we'll call E lambda of lambda to be, I'm sorry, EK of lambda to be the sum prime lambda in lambda of lambda to the minus k. So we're basically summing over all the lattice elements. The prime means exclude 0. Given that we're taking the sum of 1 over lambda to the k, we clearly cannot include 0 in the sum. What is the easiest lattice to look at?
Square.
Square lattice. So easiest is lambda equals maybe m plus in, mn are integers. And so we can study objects like this. Now, if we look at what's going on here, we really have two unit vectors. We have the vector 1, 0, and the vector, say, 0, 1 coming up like this. And when we write things with complex numbers, this would often correspond to 1, and what would 0, 1 correspond to? I. And if you think about what's going on, with the unit circle, writing things as e to the I theta, theta going from 0 to 2 pi, we have a nice correspondence between points on the unit circle and a theta. So there's one free parameter. When we're looking at our lattices, we can often adjust things a bit, and we have some freedom in how we define the lattice. Do you think you could have infinitely many vectors of length below a certain threshold?
No.
Why not?
Lattice, because you can bound the distance between lattice, like by sphere packing them or something. Like I don't know, like each two separate points in the lattice need to be actually no. Never mind.
So why do you think I'm concerned about having infinitely many points that are converging to the same length?
You need the Eisenstein series to diverge.
Yeah, we want, wait, what did you say?
You need the Eisenstein series to converge.
We want it to converge, right? I couldn't tell with the mask if you said converge or diverge.
I said diverge. But
Oh, you did say that. Okay, so I
but
didn't hear.
we don't want it.
We don't want it to diverge, so we want to make sure it converges. So the fear is, if we have a lattice, we want to make sure for this sum to have a chance of converging that we don't have a string of vectors that are converging to, say, the zero-length vector. Or if they're all converging to, if we have a sequence that's converging to a vector of a fixed length, that's equally bad. You know, if we could have infinitely many such things. And so you could maybe start playing some games. If you have a bunch of vectors that are converging to the same thing, if you look at their difference, you have a set of vectors converging to zero. And then we could get things arbitrarily small. We could make this blow up. So what do we mean by a lattice? So fix V and W, and then the lattice would be the set of, say, MV plus NW, M and N in Z. Anything else I need to assume?
V and W are independent.
Yeah. V, W, linearly independent. I would have said the exact same thing as you, but that's a little bit lazy. Linearly independent over what?
The vector space Lie, like they're not multiples of each other.
So could they be a real multiple of each other?
No.
So do we want them linearly independent over R?
Over R, I think, yeah. Oh, over C.
Or is it over C?
Over R, yeah. Over C, it's
Over Z, clearly. Over Q, clearly. What would happen if they were not linearly independent over R? So if you had, V equals R times W. This would be a one-dimensional object.
It'd be two-dimensional over Z, technically. Still, because you could have.
But they're in the same direction.
Yeah, but like as a vector space over Z.
So as a vector space over Z, it would be
Yeah.
it would be two-dimensional.
Yeah.
But it would be geometrically aligned. And so when we're looking at this, we want to have something that's filling up the plane. So we want B and W to be in two different directions. And so linearly independent over R. So they're basically two different directions. And so then the question becomes, if I give you two different directions, is there a minimum length of the possible vectors? Yes, there is. If you look at M and N, there's clearly a vector of minimal length. What is the vector of minimal length? Doesn't matter what B and W are. You range over all, I'm sorry?
Zero.
Yeah, the zero vector, right? Clearly, zero has smallest length. The length has to be non-negative, and zero is the smallest thing that can happen, and it happens. So then the question becomes, is there a next smallest? And how many vectors could have that length? And so if I give you two linearly independent vectors, can you say what the second smallest length would be? Could that get arbitrarily small? Or another way of looking at it So here's R, and there's lots of ways of doing it. And maybe this is R, so this whole thing is of length 2R. How many vectors do I have of length between R and 2R? Because if I have some count for that, I can try to figure out when this sum converges. Because if I'm looking at the size, if I take absolute values, I just care about the length, and I just want to have some estimate for how many could be in this range.
Roughly r squared.
Why R squared?
Because with, I mean, just if you look at the volume of each like circle,
Right.
it grows as r squared.
So the volume grows like R squared, so this band will have area R squared. So the hope that the length of lambda in R2R may be on the order of R squared mn. Does that seem a reasonable conjecture? Is there any lattice where we could test this?
The integer.
Yeah, take the integer lattice. So if we take the standard integer lattice, we want R squared to be less than equal to m squared plus n squared less than equal to 4R squared. Right, because we want the point m plus in to have norm between R and 2R. So how many pairs m and n will work? And again, this is where we start to do analytic number theory. For a lot of analytic number theory, we don't have to get the best answer. We just have to get order of magnitude.
At most 4r squared.
So the hope is at most 4R squared. We can say, look, we know clearly m squared plus n squared is less than equal to 4R squared. Forget about the lower bound. This tells us m squared is less than equal to 4R squared. So you immediately get m, an absolute value, is less than equal to 2R, and n in absolute value is less than equal to 2R. Therefore, at most, how many?
It would be like 4r plus 1 squared.
Yes, because you have to remember the 0, which is so annoying. So it would be 4R plus 1 squared. Has everybody seen big O notation? Yeah. Everybody has seen big O notation? Okay, good. So this tells us that the number of points in one of these bands is of size order R squared. And in fact, you could prove that there's a lower bound, that there's at least R squared things that work as well. So what does that tell you about K? If we want this to converge, so we want the sum of 1 over m plus in to the k, mn goes from minus infinity to infinity, excluding the pair 0, 0. So if we take absolute values, this is less than equal to the sum of m and n. We'll have 1 over m squared plus n squared to the k. And then what we can do is we can do a dyadic decomposition. And we can say, how many of these have norms between 1 and 2, 2 and 4, 4 and 8, 8 and 16. So do a dyadic decomposition. There'll be a sum. K goes from, say, 0 to infinity. Number of pairs with norm in 2 to the k, 2 to the k plus 1, divided by, and then the best thing to do is to make it as small as possible. Oh, wait, k is a horrible, horrible letter to use here. Right, why is k a terrible letter to use?
Because we're gonna have K for
It's k is the weight. So I can't use k over here. I can't use m, I can't use n. Let's use L. 2 to the L, 2 to the L plus 1. So the sum is largest if we replace everything in this band with the smallest possible norm, which would be 2 to the L to the k. And now, so the double less than means, has everybody seen the double less than notation?
Much smaller than?
Not really. Double less than means that it is, the absolute value of this is less than or equal to a constant times what follows. It's the same as the big O notation.
Oh.
It's another way of writing big O. If you have 3 less thans, I think some people do use that to be smaller than. But this really means no larger than a constant times. And so we would have a sum. L goes from 0 to infinity. How many do we have of size, 2 to the L? It was like 2 to the L squared. So we'd have like a 2 to the 2L divided by 2 to the LK. So what do we need for this to converge? This is just the sum over L of 1 over 2 to the L minus 2 times K. Oh, sorry, K minus 2 times L, sorry. I was about to say, the geometric series is not going the right way. So it's K minus 2 times L. So this is a geometric series with x, so we have a geometric series where R is equal to 1 over 2 to the k minus 2. So what must be true about k?
K is greater than 2.
Be more specific. K greater than 2 is enough for it to converge, but we were always assuming that k is an even number. So this actually will tell us k must be at least 4. But the sum will at least converge. So this is the most progress we've had so far in terms of trying to find something. So I'm thinking about whether or not I want to make it as a homework problem or just something that I encourage you to do to prove that you have a growth rate as claimed for more general lattice. What we're doing is we are looking at one special lattice. You could look at some other lattices to try to build up some intuition. And I can't stress enough how valuable it is when you have problems like this to spend some time on a lattice you know. What other lattice might you do?
Hexagonal?
Hexagonal. The hexagonal lattice occurs so often in sphere packing. We've seen the value it has in the plane, that's another great one to consider. It's also not aligned with the coordinate axis, so you at least have a little bit more interesting behavior. So I would try to do these calculations for the hexagonal one as well. All right. So does anybody know what the most valuable log is in all of mathematical proofs? The W log. What is the W log? Without loss of generality. So we did a lot of that when we were looking at, one of the papers of the hexagonal lattice is the best in the plane. We want to try to do something similar when we're studying our lattices. We have two vectors. Without loss of generality, one of them has to have length at most out of the other. So let's say we have V and W generate the lattice, and V is less than or equal to W's length. What do we know about V's length without loss of generality? 1. Without loss of generality, the length of V equals 1. We can just change our scale. What else can we assume about V?
Upper right plane, right quadrant.
We could do upper right quadrant.
It's just the real number 1.
It's just the real number 1. We have a choice as to where we want it to be. We might as well take V to be going from 0, 0 to 1, 0. This should be very similar to what we did weeks ago when we were doing the hexagonal packing. What can we assume now about the other vector? Okay, it has to be in the upper right. And the upper right could include straight up. What would happen if it was like this?
You could just add V to it.
You could add V to it and push it into here, and it will still generate the same thing. The only thing you have to be careful about is you have to make sure that it has a length that's at least as large as 1, 0.
You just add V twice then.
Right, so if necessary, you add V twice or 3 times or 4 times, and it will generate the same lattice, because then you can always just subtract things off over there. So without loss of generality, we can always push it into the upper right. If it was down below, we could take its negative, and that will put it up. So we can assume W in the upper right quadrant. And so something like that. And so we can represent this as a complex number, and we'll often use tau to represent the complex number that we have it. So we're representing the vectors as x plus iy. So this would be 1 plus 0I. This might be wx plus I wy. And now I can basically associate to this lattice this complex number tau. And I will have the sum over m and n that are not 0, 0 of 1 over m plus n tau to the k. And so we're going to try to construct a Eisenstein series here. And this is where I hate the notation because it always, right, so here k is an even integer. And so I think I want to do a search and replace. What do you think I want to replace k with? 2k. So let's replace k with 2k. And so we come over here, we put a 2 there, we put a 2 there, we would have a 2k minus 2, we would have a 2k there, 2k minus 2, and we would get 2k greater than equal to 4. And then it should be a 2 there as well. And this is one of the problems is that, you know, different people have different conventions. Some people just say, well, you'll use k, but k will always be an even number. And other people say, well, that's kind of confusing because you're going to make a mistake somewhere. If k always has to be an even number, let's just write it as 2 times k and be done with it. And so we want to know whether or not this will converge. And so the hope is that a very similar calculation to what we did before will show that this converges for 2k greater than or equal to 4. So encouraged to show converges if 2k is greater than or equal to 4. We did the special case when tau is just I, and that was the square lattice. So what do we hope is true about this function? So what do we hope is true? Hope ek of tau is the sum, mn not being 0, of 1 over m plus n tau to the 2k. What do we hope about this? So what's the hope?
So the number of terms between r and 2r are the same? Are going to be the same value?
Well, that's for convergence.
Okay.
And so I've already wrote that we're encouraged to show that this does converge. We can do that, or are you willing to just assume that this is very reasonable? We should be able to modify the arguments we have. You know, tau is a fixed direction. We're not going to have this issue of having too many points inside a band, that it should grow like r squared. Let's make that homework. That's a good homework problem. What do we want to be true about this function? It exists, which is a great thing for a function to be. What kind of function are we looking for? A cusp form, a modular form. So we want to show for all gamma in SL2Z, ek of gamma tau is CZ plus D to the 2k ek of tau. How should we do this? So do we want to write down, let's take an arbitrary A, B, C, D and just do the algebra? Should that be possible?
Yeah.
If it's true, yeah.
If it's true, yes. And so since it's true, we should be able to just plug in gamma equals A, B, C, D, go through here, go through all of the manipulations, and show that at the end of the day, we get back to where we started. So proof 1, brute force, with gamma being A, B, C, D. I don't want to do that brute force. Is there a better way to prove it? Do we have anything in the bank that will help us? If not, we're going to have to do this for an arbitrary A, B, C, D.
Oh, you can use the generators on.
Yes!
Yeah,
We can use the generators, right? That was the whole purpose of proving that SL2Z is generated. Proof 2. SL2Z is generated by S and T. T is 1101. S is, I think, 0, negative 110. All we have to do is prove that it works. All right, there's 2 calculations to do. I'll do one, you do one. Does that seem fair? What do you need to know to see if that is fair? There's 2 calculations to do.
Problem's probably quite a bit easier.
Yes. Do you want to go first or second?
Well, we want to go first, so we decide which one.
All right. Let's see. I think I have a coin on me. So I will flip a coin. Who's going to call it in the air for the class?
I can call it.
All right, Clay will call it. Do you want? All right. If you're correct, you get to choose what you want.
All right.
I think we should make sure that everybody can see the coin independently. So I will toss it near you.
Heads.
All right. Can you check and see if it's heads or tails?
It's a head.
It's a head.
Indeed.
All right. Now I will walk in sight. Well, yes, if you were. I confirm that it is heads. So you have won the coin toss. What would you like to do?
So, I think T is much easier.
You guys want T?
Like, if you look at the formula, it's 0, Z plus 1 to 2.
Well, I don't know.
So when you look at EK
You want X.
of T tau.
Look at the modular form.
Oh, you want the more challenging one?
So you do S, we do T.
Yeah. Bill Cosby has a funny skit about the Revolutionary War as a football game, and there's a coin toss, and the colonials win. They like to wear, jungle colors and hide in the woods. British will wear red and march straight down the streets. And you can guess how it goes for the British. You definitely want to do T. So EKTZ would now be the sum over MN 1 over M plus N T tau to the 2K. And so what does this become?
Tau plus 1.
Tau plus 1. So this becomes the sum of M and N, oops, not 0, 1 over M plus N plus N tau. To the 2K. All right, now what?
Change your variables as mission.
Okay.
Or actually,
So the question is, do you hit every pair, say, A, B, except for the pair 0, 0? So when we look at the initial sum,
I think so.
because in this special case, for the matrix T, CZ plus D to the 2K is just 1 for T. And for S, C is going to be 1, so it would just be Z to the 2K, I guess, CZ plus D to the 2K would just be Z to the 2K. Right?
be negative 2 or
Oh, no.
No, because C is 1, D is 0. Right?
Yeah, no, that's good.
And if we had switched the 1 and the negative 1, if we put a negative 1 down here, it wouldn't matter because we're raising it to an even power. So your factor CZ plus D to the 2K is just 1, so you have to show that this is the same as the original sum. So how do you show it's the same as the original sum? So must show the sum mn of 1 over m plus n tau to the 2k is the same as the sum mn prime 1 over m plus n tau to the 2k. So how would you show that these are the same?
So we know that like m and n can have any value, right? So
Well, no. M and n can have every value, but it can't be the pair 0, 0.
oh, it can't be the pair 0, 0.
It can't, right. So this is basically all mn in Z2 say for 0, 0. And so everything in Z2 is hit once and only once. So how do you finish the proof?
Can you just show that m plus n, that's everything in C2?
Yeah, so what we want to do is, given
But
a, b not equal to 0, 0, show there exists a unique pair, maybe mn, not equal to 0, 0, such that m plus n is ab. All right, this is not that bad. You take n equals b, and m is going to be a minus b. Is there a danger that this could be the pair 0, 0?
no.
Why?
No, because b would have to be 0, and a minus b would have to be 0.
Okay, to be 0, 0, need b equals 0, which then implies that a equals 0. Is that? Or if we want this to be 0, so b would be 0, so n would have to be 0, and then m would have to be 0. So I may have written it poorly, but I think it's understood. So we can get any pair AB essentially just by translating m. Is it possible that two different mn's could give us the same AB? No. Because they have to have the same second component, and then once you subtract that, then you get the first. So we have basically a one-to-one onto map from z2 minus 0, 0 to the m plus n with mn not 0, 0. So it's the same sum. So we've handled that case. Okay. So any questions about this part? So the last thing we need to do is we need to now handle what's going on when we take s instead of tau. I'll keep most of the stuff the same, so this is case 2. We have s tau. So this becomes an s tau over here. And so we get a sum of 1 over m plus, sorry, it's going to be minus n over z to the 2k. Because s of z is negative 1 over z. Except, of course, we're not using the letter z, we're using the letter tau. And this is the problem with everybody having their own notation as to what they're doing. Fine, not a big deal. Okay. So let's study. We've got the sum over mn not 0, 0, 1 over m minus n over z to the 2k. I know what I'd like to do. Yes?
Multiply through by z to the 2k.
Multiply through by z to the 2k over z to the 2k. So we have z to the 2k over z to the 2k, and then we'll get a sum over mn prime z to the 2k, and then we have 1 over mz minus n to the 2k. Well, as n ranges through everything, can I replace negative n with can I replace n with negative n? Yes. So this is the same as z to the 2k sum mn prime 1 over n plus mz to the 2k. Well, now I'm just switching the roles of m and n. It's still the same function. And this over here is just, sorry. This is exactly the factor we wanted. So the z to the 2k e k of tau. And this is, cz plus d to the 2k from a, b, c, d equals s. So the calculation actually is very easy to do like this. You could ask, how much worse would it have been to do the general case? If you now have, instead of having s tau, if you had a tau plus b over c tau plus d, you would multiply through by c tau plus d over c tau plus d to the 2k. And you can say, oh, that's exactly what we wanted. So the more general calculation, the sum of mn prime 1 over m plus n a tau plus b over c tau plus d to the 2k, you multiply by c tau plus d to the 2k over c tau plus d to the 2k. And you can see there's the c tau plus d to the 2k that you wanted. And you have a sum over m and n. And you'll have, when we multiply through, you'll have mc tau plus an tau, mc plus an tau plus, we'll then have md plus nb. And make the whole thing to the 2k. So what do we have to show now?
Whoa, we?
Yes, I did case 2. I did S. We each did one case. We're back on the same team now.
Let's
Yeah.
flip another coin.
Where's that Mobius coin I brought? What would we have to do now?
Show that goes over all integers.
So that this goes over all integers. So that there's one and only one solution. So if we look at maybe solving, m tilde is mc plus an, and n tilde is md plus bn. This would be the same as ac dB mn equals m tilde n tilde. So that'll give me, did I do it wrong? I think I did it wrong. I want MC, C and A is switched. All right, now you get MC plus AN equals M tilde, MD plus BN equals N tilde. So what we want to do is we want to show, you give me any pair M tilde, N tilde, I can find an MN. So is that matrix invertible? What's its determinant? Negative previous, so its determinant is -1. So you get MN equals CADB inverse N tilde N tilde. And we can show that we do have this nice one-to-one correspondence again. It's essential that these elements here are integers and that the determinant is of absolute value 1. So determinant is -1. Which proof do you prefer? This proof has no case analysis. And this proof does not require you to know what generates SL2Z. So in terms of if all we wanted to do was just get straight to the proof, this is a faster approach. The algebra is not that bad. And this is the power of linear algebra, of trying to find what's the right way to look at things, what's the right coordinate system to do. These are really nice transformations. That said, it's nice to know how SL2Z is generated. It's nice to be able to break up a complicated thing into a simpler one. I prefer the case 1, case 2, especially given how trivial it is with T. It's just translating things. Not to say that you guys didn't have a great contribution in class today. It was wonderful. Was S that hard? No, S wasn't that much worse. This is a little bit harder. We have to just do a little bit of bookkeeping, but it's not horrible. So we've now shown, modulo that homework problem that I gave you, that we can construct modular forms. That they will converge, they'll be differentiable, they'll have wonderful properties. And it all comes down to just counting how many things can be in a region. And we can take circles or annular rings of increasing size. Yes?
Doesn't this only show modular forms for weight k greater than or equal to 2? And then we showed k equals 0, which is constant. So
Right.
we know k equals 1.
Or so k equals 1 would correspond to k equals 2. So I believe that space is empty. And so all of these spaces are finite dimensional. And there's one where one of the best proofs in mathematics, it involves the Ramanujan tau function. You want to show its coefficients have a certain property. You show that modular forms have this nice property. And you show that the weight of this modular form corresponds to a space of modular forms of dimension 1, which means all the forms have to be a constant multiple of this. And so if you normalize them to have the leading coefficient being 1, they must be identical. And then you win. And so it's very rare that you have a space that only has one element. It only has like one direction. But in that situation, there's a tremendous amount you can do. So if you know some complex analysis, and maybe I'll send the notes from C as a course in arithmetic, outstanding book, which goes through and computes what are the dimensions of the different modular spaces. I wanted to just do enough here to highlight what is the emphasis of what's going to be happening to us. We can always write down conditions. When are these conditions going to be compatible with the existence of some function with these desired properties? And that's what the sphere packers needed, is they needed to find a function that had a certain set of properties. And that's what we're moving towards now. And so in the next class, we'll talk more on lattices, Have you guys talked about the dual lattice yet? Have you seen that in any course? Usually it's not covered. All right, so we will do the dual lattice on the next class, and we'll talk about, well, how would you generalize the Fourier transform if you had a function of many variables? And if you have a function of many variables, what kind of function do you think might be nice for sphere packing? What might you want to assume about your function? So clearly we want it to be continuous, differentiable, have nice decay. But what might you want to assume about a nice function in say 3 variables, 4 variables, 5 variables? What do you want it to depend on? You want it to depend only on the
Lattice.
well, not the lattice. We're going to think of something in either x, y, z space or rho, theta, phi space if we're doing things in 3 dimensions. What kind of function would you want in rho, theta, phi space? It depends on only rho. It only depends on your distance. So those would be called radial functions. If only on rho, it's a radial function. Can anybody give me a function from physics that's extremely important, that's radial, that only depends on your distance?
Force of gravity.
Force of gravity. Right. All that matters is it's 1 over r squared. You could do electricity and magnetism. Electricity 1 over r squared force. We're doing the non-relativistic versions of these. All right, so this is a good place to stop. Have a great weekend.